Hello again. We are continuing our discussion of limits by talking about calculating the area underneath specific curves or functions. All right, so here's an example. We need to approximate the area between the x-axis and the curve y equals x squared plus 1 from x equals 1 to x equals 4. All right, so I don't know what the formula for that area is, the best I can do is approximate it. What I can do is I can find the left-hand sum, and I'm going to do that by making rectangles where points from the curve are in the top left corner of that rectangle. Okay, so those are 3 points I can use, those red dots there, and I can build rectangles off of those points, making sure those points are in the top left corner of the rectangle. And then I can find the area of those rectangles. And the first rectangle is 1 by 2, the second one is 1 by 5, and the third one is 1 by 10. So that gives me a total area of 17. Now you'll see that that's an underestimate of the actual area under the curve. So maybe I want to do something else to try and get a better approximation. I can find the right-hand sum, and I can do that by making rectangles where the points from the curve are in the top right corner. Okay, so those are the points I will use. And I can make rectangles where those dots are in the top right corner of the rectangle. And so now the areas are 1 by 17, 1 by 10, and 1 by 5, and that gives me a total area of 32. So I know that that's an overestimate. You can tell because I've basically covered up that entire portion of the curve with those rectangles. So 17 would be an underestimate for the area, and 32 would be an overestimate of the area. So what I can do is I can find an even better estimate by averaging those together and getting 24.5 as a better approximation for the area between that curve and the x-axis. All right. So this leads us to a discussion of what the definite integral actually is. We're not going to get more detailed than this until we start talking about integration specifically a few chapters down the road. But here's an example. Let's consider some function like this. And if I approximate the area using rectangles, each rectangle is going to have a width of delta x. Now you remember delta y and delta x from Algebra 1 when you were talking about slope. So that small change in x, whatever it happens to be, whether it's 1 like you see in this picture, or it could be smaller, we're just going to call that delta x. All right? The height is going to be whatever f of x is for that specific x value. All right, so the area of each rectangle is the function value for that x times the change in x from one rectangle to the next. So the sum of the areas would be the sum of those f of x's times the delta x's. All right, so in order to make that a better estimate, what I could do is I could use more rectangles but make them narrower so that delta x becomes really, really small and the number of rectangles becomes really, really big. And I can see what happens. Remember, we've been talking about limits. I can see what happens as the width of the rectangles approaches 0 and the number of rectangles approaches infinity. And when that happens, I use a special symbol, that funky S-looking thing. That's actually the symbol that represents the exact area from x equals a to x equals b of that function. You're going to see that, like I said, you're going to see that more a few chapters down the road. But what that means is I'm looking for the exact area from some x to some other x of the function. I'm looking for the area between the function and the x-axis. All right, so that's what that symbol means. Sometimes, though, I'm given a situation where I can find the exact area and I don't really need to approximate. So take a look at this linear function right here. Let's say I want to find the exact area from x equals 2 to x equals 8 between the function and the x-axis. Well, if I draw it, it's a trapezoid, and I know how to find the area of a trapezoid. The average of the bases, which is 7 and 4, times the height of the trapezoid, which is 6. And that gives me an area of 33. That's the exact area. I don't need to approximate it or anything like that. All right. And then my second example is this semicircle function right here. Not going to write out what the function actually is, but you can see that it is a semicircle, and I want to find the area from 2 to 6. Well, I know that it's a semicircle, so I can go ahead and find the area of it it is a half times pi times 2 squared, which ends up being 2 pi. So that function has an exact area of 2 pi as I go from x equals 2 to x equals 6. We're going to have more examples of this tomorrow, but if you have any questions in the meantime, please let me know, and I will see you tomorrow.